everyone, welcome back to alkaline hydroxide 784, and today it is the first episode of the chemistry series. Since we're just going to cover the first topic, which is atomic structure. I find it funny that that's the only topic in the first core idea, so yeah, like after that is immediately the second core idea, so I don't know how this works. But anyways, that's the topic I'm going to cover. I think it is, I guess it could be quite boring for some people, but it is a very important topic nevertheless because it underlies a lot of the other topics that you learn in chemistry, and it helps you understand the other topics a bit more. So you need to understand how the atom, like the structure of the atoms, how they work and all that before you can understand many other things. So yeah, let's get started. So like how I did in the physics series, I'm just going to go through the learning outcomes, and I think I remember this topic being mostly explanation, so all the those 3-4 lines of explanation for each thing. So I think it shouldn't be that hard to go through this topic. Yeah. Okay. So the first learning outcome is about the protons, neutrons, and electrons in terms of the relative charges and relative masses. Well, this can be very easily summarized in the little table. You write your proton, neutron, and electron, and their relative charge: proton is positive, electron is negative, and neutron is zero. It's like neutral. That's why it's called a neutron. Like proton is like positive, so it's pro. Electron is negative. I don't know. I guess that's pretty easy to remember anyway, so you don't need any hints on how to remember that, I guess. And the relative masses. Okay, a proton and a neutron are each 1 AU. AU not as in not academic unit, but atomic unit. Sorry, arbitrary unit actually. I don't know. It is that thing that represents the mass of one proton or one neutron, and it's there in the data booklet somewhere, so yeah, you can just look at that yourself. An electron would be 1 over 1960 of that, I guess. I don't remember the number. I guess you don't really need to remember the number though, so it's not that important. But you do need to know that electron is a lot smaller than a proton or a neutron, and when you look at the MCQ question, you can kind of tell which number it is. So if you look at the, important values and constants and standards in the data booklet, you can actually see the mass of a proton, neutron, and electron right there. So if you're a bit confused about the exact number, just divide it in your calculator and you get the answer. So yeah, should be okay. You will be fine. Anyway, let's go back to the rest of the learning outcomes. It takes a lot of scrolling up and down. Okay, so the second one is the behavior of protons, neutrons, and electrons in an electric field, specifically a beam of one of those things. So in the physics series, there was this there's one chapter where we talk about a charged particle going through an electric field. Well, it's pretty much the same thing. So you imagine an electric field formed by a positive and negative, parallel plates kind of thing. And the protons would be obviously attracted to the negative thing, the neutron will just be going straight, and electrons will be attracted to the positive thing. We ignored mass of them because their mass is quite small, so it doesn't affect it won't change distance that much due to the mass. Most like the charge is more likely to change the direction more than their mass or their weight for that matter. So yeah, that's the general idea. I think I would have drawn it by now. Okay, so the third learning outcome: distribution of mass and charges within an atom. Right, so an atom is, well, basically the middle of the atom has the protons and neutrons, which we would collectively call the nucleons. And these nucleons create the nucleus of the atom, so it's in the center. And the electrons kind of, zoop, zoop, zoop around the nucleus. I mean, I say that instead of saying it orbits around it because it obviously doesn't just orbit or something, it moves literally in random directions around the nucleus, so yeah. So the mass of the atom is very concentrated in the center because the distance between the nucleus and the electron is probably way bigger than the size of the nucleus. Yeah, the atom is very concentrated in the center, and the charges are balanced through the the charges work like this, like the positive is all in the center and the negative is around the nucleus, kind of. Yeah, that's pretty much how it works. And in order to prevent internucleon repulsion or inter-electron repulsion, there's some sort of arrangement, like some kind of separation between the electrons or between the protons by using, I guess, the neutrons help. And there's also some other factors that allow them to still stay together, one of which is the strong nuclear force. So yeah, cool. Anyways, so the next one, describe the contribution of protons and neutrons to atomic nuclei in terms of proton number and nucleon number. Okay, this is pretty simple. Proton number is, well, the number of protons in an atom, and I'm saying atom because you're talking about atomic nuclei here, so yeah. And if you look at your periodic table, you have both the proton number and the nucleon number in your periodic table. So let's say if you look at hydrogen, for example, the top part is actually the atomic number, which is actually the number of protons in that particular atom in a sense. And if you want to know the number of neutrons, you can look at the relative atomic mass and round it up to the nearest whole number. That will be pretty much what is the nucleon number. And if you minus a proton atomic number from that, you will get your the number of neutrons. But of course, you do know that there's isotopes, and different isotopes have different numbers of neutrons because the neutron doesn't really change the identity of the element. It's the proton number that actually determines the identity of the element. So please do take note of that. So once again, scrolling back to the thing. Okay, yeah. Oh yeah, the next part of the second part is about isotopes actually. So before we talk about that, proton number is number of protons, nucleon number is number of protons plus the number of neutrons, and atomic number is basically the proton number. So yeah, cool. So how to distinguish between isotopes? Well, simple. There's different numbers of neutrons in it. Well, that's the simplest way to do it. Yeah, that's it. Of course, if there's different protons in it, they are no longer isotopes, they're different elements. Or maybe actually, yeah, they're different elements. It can be anything else. So yeah, isotopes have the exact same number of protons, but they have different neutron numbers, which would lead to different nucleon numbers as well. Okay, cool, let's move on. So describe the number and relative energies of the Sp and D orbitals for the principal quantum numbers 1, 2, 3, and also the 4s and 4p orbitals. Okay. So we have all these different orbitals, and if you look at the periodic table, it helps a lot. And so this is about the number and energies of the orbitals. So the one with the lowest energy is the 1s orbital, it's the closest to the nucleus, I guess. And of course, each orbital, the 1s orbital has 2 electrons in it, so that's pretty simple. And and if after 1s you get 2s, this is another s orbital, and that will also have 2 electrons. And after 2s you get 2p, in which you can get 6 electrons, and after that you can get yeah, then if you go to 3 you get 3s, 3p, and 3d. So d will have 5 sorry, not 5, 10 electrons. So yeah, cool. And then you have 4s and 4p. I think you get the idea. So for s is usually you add 2 electrons, p you add 6 electrons, and d you add 10 electrons. So the s orbitals generally have a lower energy than the p orbitals, which would generally have a lower energy than the d orbitals. But the easiest way to see which orbital has a lower energy is by writing down the 1s. Like you write 1s, then you write 2s, 2p below it, and then you write 3s, 3p, 3d below it, and then you write 4s, 4p, 4d, 4f. Okay, I don't think you really need to think about the f, but that's basically how it works. And then you draw an arrow diagonally downwards. So the one at the lowest energy is 1s, and then the second one at the second lowest energy is 2s, and it's 2p, and then is 3s, 3p, 4s, 3d. The reason is because when the 4s and 3d are very close in energy, so it is very likely that the 4s is, when filled, like when the 4s is filled, it tends to have a lower energy. Wait, no, am I saying something? No. When the 4s is empty, it has a lower energy than 4d, so it tends to be filled up first. But once the 4s orbital is filled, it tends to have a higher energy than the 3d orbital. And if you don't want to write this down and accidentally get it wrong, you can just look at your periodic table. You know that your periodic table has the S block, which is the first and second periods, I guess. Sorry, not period. Sorry, first and second groups. I don't know why I said period, I'm so sorry. The first and second groups, that's the S block. And then if you have the transition block, which doesn't seem to have any numbers written on the top, but they're actually the third until the 12th group. And then the 13th to the 13th to 18th group is actually the P block. Yeah, so the transition part is the D block, and the thing below is the lanthanoids and actinoids is the F block. That's pretty much it. So when you want to see the how the electrons fill up for each element, you can actually look at it through this by reading. If you look at it horizontally through the periodic table, you can actually see that the 4s comes before the 3d, if you think about it. So let's say if you look at the first two, this is 1s, H and helium. Then lithium and beryllium is 2s, and then boron to neon is 2p. Sodium and magnesium is 3s, aluminium to argon is 3p, and then potassium and calcium is 4s. 4s comes first. But please don't write 4s first on when you're writing the orbital thing, when you're supposed to write 1s1, 2s2, please don't write 4s before 3d, because when you write it in the right order, but when you are explaining, you should realize that the 4s orbital is filled first, and it's also emptied first when you remove electrons. We'll get back to that in whatever topic that's applicable. So yeah, the potassium and calcium is 4s, and then scandium to zinc is 3d, and then gallium to krypton is 4p, and so on and so forth. So that's how it works. Yeah, that's an easier way to actually figure out which one comes first. Yay. Okay, let's get back to the learning outcomes. Alright, so what are the shapes of the Sp and D orbitals? Okay, so oh yeah, I'll just tell you how the numbers work with regards to the electrons while telling you about the shapes. Okay, so the s orbital is just a spherical shape, so that's pretty much it. It just looks like a sphere. And so if you need to draw, you just draw a circle and that's it. Yeah, just draw the axes and the circle. So for the p orbital, there's actually 3 different p orbitals, and there's p pxy, pyz, pzx, or xz, sorry. So what that means is you have to draw it in regards to the axis, basically. So if it's xy, you would be drawing, you know, within the xy and x-axis and the y-axis. And if it's yz, you draw it in the y-axis and the z-axis. And if it's like xz, then you draw the x-axis. Wait. Did I do something wrong? Oh yeah, sorry. It's not on the axis, but in between the two axes. So like if you think of the xy axis as a plus, you draw the orbitals like imagine it as an x that's in between the plus, the spaces between the 4 quadrants. And likewise you do that with the other 2 p orbitals, and you will get the 3 different p orbitals. And for the d orbitals, there's actually 5 of them. So where was I? Okay. So for the d orbital, you have the x square, y square, and then I think I need to write it down. Sorry, I'll just write it down, and then you will see what are the 5 different d orbitals. So for the p orbital, it's actually only one. It's like one barbell, and for d orbital, it's actually the x configuration thing. My mind is a bit confused. That's why I said it wrongly. I'm so sorry, but I'll draw it properly. Don't worry. Yeah, so the p orbital kind of just looks like a barbell or dumbbell, whatever. And then for a d orbital, it looks like 2 of them, except for the last one, which is one dumbbell surrounded by a donut. Yeah. So the next learning outcome is the electronic configuration of atoms and ions given the proton number and charge. Okay, yeah, this is the part I was talking about, electronic configuration. When you write your electronic configuration, you had to write it in numerical order. Please don't write for S3D. Like, don't do that. But you must realize where the electrons are. So if there's no electrons in 3D, then you don't need to write 3D in a sense. Yeah. So let's say, okay, I'll just give a few examples and we'll see how it works in a sense. I'm just looking at the remaining learning outcomes so I can see if there's anything that I need to, figure out. Okay, cool. So let's go through the stuff that doesn't have that many exceptions. So let's say we go to boron. What's the electronic configuration? Actually, no, let's not do boron. let's just okay, let's look at the 4s part. Okay, so if we are looking at calcium versus candium, if you're looking at calcium, we will have, you'll be writing all the 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. You don't write any 3D. And if you're looking at scandium, you'll be writing everything except that there's a 3D1 and a 4s2. That's the difference. But when you're looking at a scandium ion, like scandium plus, you remove it from the 3D or the 4s? You remove it from the 4s first. So you have 3D1 and 4s1. That's pretty much what happens. But if it's just calcium ion, then you don't have to really worry because it's pretty straightforward. But once you get into the D territory, you need to be a bit careful about where you remove the ion from first. So if you're looking at something within the D block and you're looking at an ion, like cation ion, then you would need to remove the electrons in the 4s orbital first before you touch the 3D orbital electrons. So just remember that. And there's also some exceptions, which is why I was a bit hesitant to look at, that boron, that area there. So the two exceptions are between the group 2 and group 13 for second. I think it's supposedly for all the periods, but mostly you look at the second and the third period. So it'll be beryllium, boron, or magnesium, aluminium. So magnesium, aluminium feels a bit more familiar, so I'll just use that as the example. But actually that one is not really related to this topic. It's more of the ionization energy, so yeah, there's nothing much. Okay, sorry. So that's why this doesn't really apply to just ignore what I said for the last 30 seconds. I'll be talking about the exception for this one first. Okay, so for this topic specifically, the actual exception would be in stuff like chromium and copper, basically, because they have this almost there but not there, that kind of property, you know what I mean? So if you were to think about it in the normal sense, for chromium the electronic configuration would be so on and so forth and so on and so forth until 3D 4 for S2. But since chromium is almost manganese in that sense, like it's almost there at it has like 5 different D orbitals, right? And one of them is empty, but the 4s orbital has 2 electrons. So it would be actually beneficial for chromium to, have one of the electrons go to the D orbital. It will be much more stable that way. Therefore, for chromium, it is actually so on and so forth and so on and so forth until 3D5 for S1. That is the actual electronic configuration of chromium, I think, yeah. I mean, not I think. I'm saying that only because I'm not sure how it really works in real life, but that's what is written in syllabus, so yeah. And likewise for copper, it's almost at a full 3D orbital, and a full 3D orbital is really nice, so it would have 3D10 for S1. That's the exceptions. That's the only thing you need to worry about for this chapter. I'll talk about the aluminium and magnesium thing later when you're talking about ionization energy. Okay, I mean later is another chapter because it's solely about atomic stuff, so yeah, nothing interesting. Okay, so right, let's move on. Explain the factors influencing the ionization energies of elements. Oh, it's actually in this chapter itself. Okay, great, you get to listen to it. So what are the factors influencing the ionization energies of elements? Right. Okay, I think that the best place to go one more time is the periodic table. The periodic table is the best place to go. It's like a cheat sheet that you're literally given during the exam. It's like the best thing. And it's why I'm going there right now because it helps a lot. Okay, so the ionization energy of the elements varies according to certain trends, right? Down the group, across the period, that kind of stuff, right? So let's start with down the group. Down the group, it'll just start from the beginning and then reach a conclusion. So down the group, what happens? Well, we have lithium, sodium, potassium, rubidium, so on and so forth. And you can see the atomic numbers increasing, right? So there's more proton, there's more neutrons, and there's also more electrons because, you know, if you have more protons, you need more electrons to balance the charge. But you don't need to say all this stuff. Just say that there's more electrons and there's more orbitals in a sense. So every time you go down, you're actually increasing the principal quantum number, like 1, 2, 3, 4, 5, that kind of thing. So the orbitals are, bigger and bigger and bigger, like the outermost orbitals, where the outermost electrons are, in a sense. That's what we're looking at, because ionization energy is the energy that's required to remove one of the outermost, whatever outermost electron there is at that point of time. So you had to look at that only. So yeah, the outermost electron in each of them is getting further and further away from the nucleus because the atomic radius is increasing down the group. And the attraction between that outermost electron and the nucleus is decreasing because the electron is further away. And this is despite the fact that the number of protons is increasing. It's also increasingly further away. So the increasingly further away kind of outcompetes the increasing attraction. So what happens here is that since there's lesser attraction, the ionization energy decreases down the group. And that's pretty much it. It's very easy. Because the ionization energy is based on the attraction of the electron to the neutrons. Sorry, not neutron, the nucleus. In other words, the protons. And down the group it decreases. Yeah. Okay, cool. That's pretty simple, straightforward. Now let's look at the period across the period. Yeah. And across the period, if we look at, you'll usually be looking at period 2 and period 3. If you're looking at the general trend is that the ionization energy increases because, which I'll explain now. So as you go, towards the right, I guess the number of protons is increasing, right? And the number of electrons is also increasing. But the thing is, each successive electron is added to the same orbital. It's not going any further away. It's in the same orbital, and therefore the attraction between the electron and the proton increases. So yeah. Oh yeah, I forgot to mention this thing called shielding effect. So the reason why the attraction in down the group decreases is because of the shielding effect. So there's like the electrons in the orbitals, there's more inner orbitals kind of repel each other and they shield the attraction of the nucleus. That's why the attraction actually decreases down the group. But across the period, the shielding effect is quite constant. It's very relatively constant because you're not really changing the inner orbitals, you're only changing the outer one. So the shielding effect is relatively constant, and the nucleus is more and more attracting the electron more and more strongly, and that actually causes the radius to decrease down across the period, and along with that it increases the ionization energy of the atom across the period. Okay, yeah, that's what happens. And on a side note, that is why on the left side you have stuff that's cation because it's easier to remove the electrons, and on the other side you have anions because they prefer taking in electrons and it's very hard to remove electrons from them. And I guess that's pretty straightforward, but we'll get to that when we need to get to that. So let's look at the exceptions now, which exceptions to the general trend across the period. And the two places are between group 2 and group 13, which is beryllium and boron, or magnesium and aluminium, and between 15 and 16, which is nitrogen, oxygen, or phosphorus, sulfur. Usually they use the period, third period as the example but it works with the second period elements as well. So what for the group 2 and group 13, which we will use magnesium and aluminium for this one, the reason why it is like that is simply because it's going from S to P. So So in magnesium it is 3s2, aluminium is 3s2 3p1. So you realize that there's this extra electron in 3p1, right? It is like, if you think about the down the group, you're actually looking at more and more orbitals. Of course, here you can think of it in the same way, because within each of the quantum, number, there's like, it's like a sub kind of orbital in the sense. So the 3p orbital is of a slightly higher energy than the 3s orbital, and therefore the electron there uh will end up, having a bit more repulsion, in a sense. And the aluminium, the ionization energy of aluminium is slightly lesser than magnesium. Yeah, that's pretty much it. Of course, for silicon it's higher than both of them, so you don't have to worry about the trend after that. And if you're looking at the 15 and 16, which is way easier to explain, we're gonna use the nitrogen and oxygen, which is in period 2. And oxygen has a 2p4, that kind of, like, 2s2 2p4, and the 4 means that there's like this paired electron thing, and because of the paired electron there is a higher electron repulsion, and because of the repulsion there is lesser attraction, and the ionization energy is lesser for oxygen as compared to nitrogen. And once again, fluorine is higher than both nitrogen and oxygen. So yeah, I guess if you're asked to draw the ionization energy trends or anything like that, you might want to take note of this if you're looking at across the period. And this will also apply to when you're seeing the trends and you're asked to tell which group the element is. And that would be somewhat related to the last two objectives, which would be J and K. So in J, the objective is about deducing the electronic configuration from successive ionization energy data, and K, it is interpreting successive ionization data of an element in terms of the position of the element within the periodic table. They kind of mean the same thing, so yeah. So if you look at successive ionization energy data, this is within one element, like the same element. If you're looking at the second ionization energy, the third ionization energy. So so before we actually go to that, within the same element, we'll just look at it in terms of a general sense as well, because there could be a question that asks you to explain why the second ionization energy of this element is higher than that of another element. So when you look at second ionization energy, or third or fourth or whatever number ionization energy, you have to look at it in terms of the element that a different element. You have to think of it like a different element. So in order to prove my point, what I mean would, maybe if we look at sodium and magnesium. If you're looking at first ionization energy, the sodium one will be lesser than that of magnesium, well, if you look at across a period. But if you're looking at second ionization energy, you would be starting off with a sodium plus ion and a magnesium plus ion. And a sodium plus ion is somewhat like a neon atom. So a neon atom has an incredibly high ionization energy, and therefore the second ionization energy of sodium would be higher than that of magnesium plus, would be higher than that of magnesium, which, because a magnesium plus will be like a sodium, and you know that in the first ionization energy, neon is higher than sodium. So in the second ionization energy, the sodium second ionization energy will be that higher than that of magnesium. So think of it that way. Like, don't use the first ionization energy explanation. Look at what it would actually be, like what the sodium, how many electrons a sodium ion has, or whatever ion it is has, before you do that whole ionization energy explanation. Be a bit careful about it. Yeah, so but if you're looking at So now we'll go on to what the learning objective is actually talking about, which is within the same element. So let's say you have any random element X or whatever, or maybe you can call it J because there's no J in the English periodic table. Well, what can I say? Uh, and this element J has some data that you can see in a table. So this data will help you figure out the its configuration or something like that. If you're given the entire set of IEs of J, then you will actually know how many electrons it has. So usually they don't give you everything, but they give you the first few IEs and they ask you to find the group rather than the actual element. So how that would work is you can look at it in terms of the jumps in between successive ionization energies, and that will help you to find out which group it is in. So let's say you're looking at magnesium. I don't know why I'm so fixated on sodium magnesium, but never mind. If you're looking at magnesium, it is in group 2. And the first ionization energy is there. Then you take another electron out, it will then become like a neon. So when you try to remove the next electron, it will be incredibly hard. So the third IE will be much higher than that of the first and second IE because you're removing it from a completely different orbital, a lower orbital. I mean inner orbital. So that would cause a huge jump in the ionization energy between the second and the third ionization energy of magnesium. So when you are given the data of magnesium, you would notice that there's a huge difference between the second ionization energy and the third ionization energy of magnesium. And that would be correlated to the fact that magnesium is in group 2. So for any element that you're given, if you see the jump between number n and number n plus 1, then that element is in group n in the sense. But usually they will not give you a transition metal because transition metals are weird. So you will learn more about them when we get to transition metals, which is actually very, very far down. But they have a very unique property, so yeah. But they will usually be getting data from period 2 or period 3 because it's a bit more clear cut there. And along with the group, you can then figure out the general electronic configuration. So like it ends, so say if it's something that's like magnesium, then it ends with something S2 or something. You know that group 2 will have S2, something S2, based on their period as well. So yeah, it shouldn't be that hard, so don't worry about it. So the explanation that you use is generally the location of the jump in IE, and the fact that this means that the third electron, for example, is from an inner orbital or whatever number electron that you're looking at, the n plus 1 in this scenario. So yeah, I think that's about it. We covered all of the learning objectives. Yay! It's almost 40 minutes. I know this will take a lot of time. Even before recording, I knew it would take a lot of time to explain everything. But I hope you understood the stuff in it properly. So I'll just end off with one last thing that you can do, which since I did talk about the periodic table quite a lot, I will tell you how you can use the periodic table in this chapter when you're a bit stuck or a bit confused. So for this chapter specifically, sometimes I tend to forget something or I tend to have no confidence in my knowledge of the chapter. So what I will do sometimes is just double check that the atomic radius is actually decreasing or increasing or whatever. So what's the easiest way to do it? You can go to this segment in your data booklet called Atomic and Ionic Radii, and you can see the period 1, period 2, period 3, group 2, group 14, group 17. Okay, this is what you get lah. And you can even use this for the transition metals part as well. You can see the radii of all of them for both the atomic and ionic radii, which is pretty good. You can use this to figure out everything. Yeah. Okay, so For this chapter specifically, we are looking at atomic radii. So let's say you want to explain your ionization energy increasing or decreasing, but you forgot whether the radii increases or decreases and you're a little bit confused. Then you can just look at this, like for example, period 2. You can see that the radii is well decreasing until you reach neon. So yeah. The reason why neon's one looks very big, we'll get to that later. But the atomic radii is measured on certain premises, so you have to be a bit careful about that. But generally, you see that it's decreasing, so you know that the radii decreases, the attraction increases, ionization energy will increase as well. So if you're looking at if you're wondering why neon's one is much bigger than lithium's radii, it is because the way that it's measured here is van der Waals for neon versus single covalent or metallic for the other elements, and that actually influences the length of the radii in a way. And it's also because neon has this full orbital kind of thing, so yeah, that's what you get. If I get the chance to explain it in greater detail, I'll probably do that, hopefully. But yeah, you don't have to worry about it right now. Just look at the general trends and you get the idea. And even for the down the group thing, you can use this to figure it out, because if you look at it, hydrogen 0.0337, then then lithium 0.152 is increasing, sodium 0.186 increasing, and so on and so forth. So it's pretty obvious. So yeah, increasing radius means ionization energy decreases. So I think that's about it. My voice is not working, so I hope you found this video useful, and if you think it was too long, I guess you would have already played it on times 2 speed so that you can listen to it quickly. But yeah. If you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye!